In the previous video, I talked about the intuitive definition of limits and also went over some notation that I'm going to be using in this video. And so, well, in this video, we're going to be going over the mathematical definition of limits. And I'll try and explain the notation as I go, in case you haven't watched the last video. So, to understand this limit definition, we have to go over the topic of distances between numbers. Distances between numbers. So let's say you have a number line. Let's say you have a number line. Right? And let's say you have a point A. And the number line is for the variable x. So x can be any value on the number line. So you want to figure out the distance between x and a. So let's say x is over here, and a is equal to 5, and x is equal to 7. You can see that the distance between them, right, you have one value for 6 and then one value to get up to 7. So it's going to be x minus a. And that'll give you the distance between them. I'll do distance in blue. That gives you the distance between them, which we know is just going to be equal to 2 if you evaluate it out. It's just going to be equal to 2. Equal to 2, right? But let's say x instead was on the other side of a. So x was over here, and x is equal to 3, right? So this distance, we want to figure out what that distance is. And what you notice is if we plug it back into the same equation here, right, we would get 3 minus 5, which gives us negative 2, right? So we get the negative distance. So we get the negative distance, right? And this isn't what we want. We want distance to always be positive. So we're going to define an equation, x minus a, the absolute value, so that we don't have to worry about the negative or the positive distance. The absolute value just treats them the same and turns everything positive. So then we have x, the absolute value of x minus a is equal to the distance. So then next we're going to kind of define, it's going to be related to distances, but it's going to be more of something called a bound, or a bound on x. So let's draw out another number line here. So let's say we have another number line. And we have a again. So a is going to be here, right? And we know that, you know, this is x. And then so we know that x minus a, and if we took the absolute value of that, wrong color, x minus a, the absolute value, would give us the distance, right? But instead of talking about the distance, we'll make it an inequality. So we're going to say f of x minus a, or x minus a, is less than some constant value c, like that, right? So if we do this, we're basically saying that x can be any value, and a and c are our constants. So let's first see, so a is just this point on the number line here, and let's see what the c means here. So what we're basically saying is we have constant c distance from a. Constant c distance from a. So a distance from a forward in c, and a distance from a backward in c. So we can kind of write that as a plus c here, and then we can write it as a minus c here, minus c over here, like that. So you have a plus c and you have a minus c, and we're saying that whatever value x takes, the distance between x and a has to be less than c. So that means x has to be within, or let me do the right color, x has to be within this range of A. So x has to be within A minus C and A plus C. And if you're familiar with the line notation here, we can kind of say it like this. It's an open circle, and then a line, and then an open circle here, because it's a less than. So x is bounded to this region. That's why I called it a bound. So x has to be within this region for this inequality over here to be true. Okay, so then now that we have the understanding of distances and bounds, let's look at a graph. So let's define a limit that we're trying to solve. So we have the limit as x approaches A of f of x, right? And let's say we already did the table and we saw that the values approach L, like that, right? So then we're gonna have to define, or let's label the graph here. So we have A, and then we can kind of see from the graph that as you get closer and closer to the value of A for x, the limit is going to be L over here, right? So this is what it looks like, and we're going to define two more values or variables that we can control that are related to bounds. So let's say we have x minus A, x minus A is less than, let's say here, less than something called delta, and I'll explain what delta is soon. And then f of x minus L is less than epsilon, right? So you can see how this is very similar to the C we had before, the bound C, or the distance from A. So if we kind of recap here, we have two constants. We have A and we have L. A and L, those are constants, and then we have variables, or we have a variable x, right? And then we have a value that changes based on what x is, so f of x, right? So if we know what x is, then we'll know what f of x is. And then we have two bounds on the distance between the variable x and A, which is delta, and then the bound between f of x and L, which is epsilon, right? So then the limit definition basically uses all these values to say the following. Okay, so then these are the limit definitions, and this is the mathematical form over here, and then this is just in plain English. So then to kind of understand this, we'll go through it step by step. So the first part is here. It says for all epsilon greater than 0, right? So it's saying we can pick any epsilon, the rest should be true, right? So we can pick, let me see here, we can pick epsilon to be out here, right here. So this will be plus epsilon, so well, L plus epsilon, but I'm going to abbreviate with just plus epsilon. It'll be L minus epsilon, and again, I'm just going to abbreviate with minus epsilon. Right, and then we can pick it closer, we can pick it over here. So this is plus epsilon, this is minus epsilon, and then we can pick, even closer. We can pick closer. Just any value of epsilon that's greater than 0, the following should be true, right? So then the next part is saying for any epsilon that we did pick, we can pick, there exists a delta that we can pick. So that means you can pick any epsilon, there will be a corresponding delta, right? and we know that the delta is the bound for between x and a, and I forgot to mention epsilon is the bound between f of x and L. Then we can pick any delta, so we can pick a delta out here, plus delta, we can pick minus delta out here, right? We can pick it to be closer here or here, we can pick it to be closer here or here, right? So we picked an epsilon, then we can pick a corresponding delta such that, so that's what this line kind of means, it means such that the distance, as long as x, the distance between x and a is less than delta, it implies, right, or if the distance between x and a is less than delta, it implies, or then the distance between f of x and L is less than epsilon, right? So this part, to understand it, let's kind of go through a quick example here. So we can pick any epsilon. So let's say we picked our epsilon to be, let's say over here, so this is plus epsilon, and let's say over here, so this is minus epsilon, right? So let's see what the corresponding points on the x-axis become. So if we went all the way across here, we see the values on the x-axis end up being here and here, right? So that's what we get for picking plus epsilon and minus epsilon, right? And then the next thing it says there exists a delta greater than 0 that we can pick, right? And the important part is right here. The distance between x and a is going to be less than whatever delta we pick. So I'm just going to pick a delta right now and I'll explain why later. So let's say I pick delta to be here and here. So this is plus delta and this is the minus delta, right? And now let's go backwards. Let's see the values that we get on the y-axis. So this ends up here and this ends up over here like that, right? So then we'll go across to the y-axis, right? So we know that picking delta limits the location or the values that x can be. So x has to be within this range. Let me use, so x has to be within this range here, right? Or using line notation, has to be within this range. So x has to be here, right? And we see that if we map that to the y-axis, because f of x is dependent on x, so f of x has to be within this range then. That's the range f of x has to be within. So f of x is going to be within that range, right? So what you notice is by picking a delta like this, right, as long as x is within this delta, we see that f of x is within this range, which is also within the epsilon range that we had before, right? So that's what this statement is trying to say, is that the delta you pick, right, implies that f of x, the distance that is mapped out, is going to be less than the epsilon distance here, right? So then going back to let me erase this line real quick. Okay, going back to the first part, we're saying that now we can pick any epsilon we want that's greater than 0. So we can pick epsilon to be over here and over here from L. We can pick epsilon to be here or here, right? We can pick epsilon to be here. We can epsilon to be as close as here to L, right? For all those epsilons we pick, there exists some delta that we can pick, right? Some delta over here, in front of A and behind A. So we can pick it here, 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 here. This statement will be true to where if x stays within that range, the distance between f of x and L will be less than the epsilon that we picked, right? And so to link this back to the table example we kind of talked about before, let me draw out the table real quick. Right, so we have x on this side, and then we have f of x on this side over here. F of x on this side. And in the middle, we had the value that x was approaching, right? Which is a for us. And then on the other side, well, we have the pattern we saw before, the limit, the values that both sides would approach to, and we know that right now we're just given is L. So what we're doing here is, instead of starting on this side of the table, we start on this side and we don't guess values, we just define a bound, kind of a bound that a generic bound. So it's L minus epsilon and L plus epsilon. And on the other side, we're saying that, so here we're saying we can pick any epsilon, doesn't matter, all epsilon greater than 0, right? On the other side, we're saying that given we picked an epsilon, we can pick a minus delta, a plus delta. So we can pick some delta, right? So that a minus to a plus delta, all values from, not including a, but all values from a all the way up to a minus delta and all the way below to a plus delta. If you mapped it over to the other side of the table, right, it would be inside the range of L minus epsilon, L plus epsilon, right? So that's good. So then the goal is you can pick smaller and smaller epsilon. So you can pick epsilon equal to 0.1. You can pick epsilon equal to 0.01. Epsilon equal to 0.001, right? You can pick smaller and smaller epsilons. You can see how that starts to squeeze f of x closer and closer to the actual value of L, and corresponding delta will get closer and closer to A, right? So this is just the formal definition of a limit. It is a little bit hand wavy, but it lets us solve it without having to guess values here, or use random values like we were with the table from before, or trying to kind of eyeball a pattern to figure out what the limit is. So yeah, so that's the limit definition. In the next video, we'll go into more about how to use a limit definition and how it helps us solve limits.